Okay, the weak form usually contains two elements. Yes?
Why did you take it out? Not variation. They're both variation.
Why did I take out what?
Like, so you remove the v dw dx because v is 0 at 0 and 1.
Yes.
Isn't that also true for both vf?
For the integral of vf, actually the boundary condition doesn't really matter because I'm integrating within the domain from 0 to 1. I have no idea what the function v is.
Oh, I see.
Inside the domain, I only know the value of it at the boundary of the domain, right? So this vertical bar means the value of v times dw dx at 1 minus the value of the same function at 0. So that I know is 0. Okay, but the integral I have no idea. Okay, so this is the weak form or the variational form. So it usually contains two elements. The first element, we call it A, is a function of w and v. And the second element, we call it b. It turns out just a function of v, right, equal to 0. So A is what we call the bilinear form. And this is, of course, the linear form. So what's the difference? The bilinear form actually contains both the solution w and its small variation, right? Contains both w and v. So the small variation is actually called the test function. Let me just say a little bit about the jargon. I mean, don't really have to. It doesn't really serve anything except for when you are reading literature, you know what it means. So w, the solution, is called the trial function. And an infinitesimal variation of w is called the test function. Okay, so basically the bilinear form contains both the trial function and the test function. And the reason it's called the bilinear is because A is actually linear with respect to both w and v. Right, so if you fix w, just look at the integral of dv dx times dw dx. If you fix w, it is a linear function of v. If you fix v, it's a linear function of w, right? Which means if you double w, you double that bilinear form. If you double both v and w, you quadruple the bilinear form. All right. Well, the other term, the b, it only contains the v. It only contains the test function, right? So it doesn't contain the trial function w. F, by the way, is a known function beforehand. So f is actually a constant. It's fixed, right? It's not it's not unknown like w or v. Okay, we are going to see that this form is actually pretty significant for two reasons. One reason is that it gives rise to basically the optimization problem. Well, I mean, actually, this can translate directly into an optimization problem because this is equivalent to, I should say, when A is positive. Well, okay. So when A here is this A is negative definite, right? So when A is either positive definite or negative definite, which means I'm going to say later, which here if A of any what function u, let's say u and u in this case is always less than 0, unless u is equal to 0, right? Which this means negative definite. Okay, then this actually translates into an optimization problem of maximizing half of A w plus b of w for all w that satisfies the boundary condition. So this is the maximization problem corresponding to that weak form. I mean, the reason is basically if you take a small variation on this problem. Okay, and because A is bilinear and B is linear, a small variation to A is actually a small variation in this W plus a small variation in this W, right? So that doubles the A of W and B. So basically this half is cancelled and we get the bilinear form. And for a small variation in B, it's just the dB. So that gives you that weak form we're looking at, right? So okay, so this is the weak form, and this is the optimization problem. Okay, any questions in this process? So basically, we did just we multiplied the differential equation with the test function b, right? And we did integration by parts, and the equation becomes the integral of the equation just falls into two parts. One part that involves the solution becomes the bilinear form. The other that didn't involve the solution became the linear form, only a function of the trial function. So basically, we get the weak form. The weak form is important because on one hand, it easily is equivalent to a optimization problem. And on the other hand, actually, if you look at the weak form, when we actually restrict both W and V into finite dimensional spaces, the bilinear form is going to give us a matrix times a vector. The linear form is going to give us a vector. So the bilinear form becomes A times X, A being a matrix, X being the unknown. The linear form gives us the right-hand side B. So we solve AX equal to B. All right, so we are going to be doing this later. So don't have to be visualizing every details right now.